Welcome to Breezy Sleepy Science. Tonight, we're tracing one of science's most captivating mysteries. Did life on Earth actually start somewhere else, far out among the stars? This concept is known as panspermia, and it proposes that our biological origins might be far older and more cosmic than we ever suspected. In this journey, we'll uncover the possible vehicles for life's interstellar travel, examine the stunning resilience of tiny organisms, and review the experiments testing life's survival in the void. We'll investigate meteorites that have crash-landed on our world, carrying the complex chemistry of life, and ask if they are messengers from our true beginnings. And we'll ponder what it means if life's seeds are sprinkled not just around our sun, but throughout the entire Milky Way. If you enjoy these calm explorations of the cosmos, feel free to like this video and follow the channel, or share your own reflections in the comments below. It truly helps our community grow. For now, get comfortable, relax, and let's begin. The term panspermia finds its roots in ancient Greek, with pan meaning all and sperma meaning seed. The notion itself is ancient. Thinkers like Anaxagoras pondered if life's spark could drift between worlds. However, the modern scientific theory began with Svante Arrhenius in the early 20th century. He proposed radiopanspermia, the idea that microscopic spores, tiny and lightweight, could be propelled across the cosmos by the gentle pressure of starlight itself. He theorized that durable bacterial seeds might surf on rays of radiation, voyaging between solar systems to eventually find a home on fertile planets. The idea captivated and disturbed people in equal measure. It was beautifully poetic, yet deeply unsettling, suggesting Earth may not be the sealed biological container we assume. Throughout the 1900s, scientists revisited the theory. Francis Crick, who co-discovered DNA's structure, even mused about directed panspermia, the possibility that life was intentionally planted here by an advanced intelligence. Today, panspermia remains on the edges of mainstream science, yet it has never vanished. Instead, it has matured, evolving from sheer speculation into a collection of hypotheses that can, however difficultly, be tested. Modern space missions, sample returns, and lab experiments keep adding new pieces to this puzzle, ensuring the idea is never completely abandoned. Researchers generally describe three main types of panspermia. First is lithopanspermia, the version most grounded in known physics. Here, rocks blasted from a planet's surface during powerful asteroid impacts carry microorganisms safely tucked inside. Protected by stone, these tiny travelers might withstand immense journeys through space before colliding with another world. Studies of meteorite exchanges between Earth and Mars confirm this process is physically possible. Rocks from Mars have indeed landed here, and vice versa. The second type, radiopanspermia, is Arrhenius's original vision. Spores or cells, small enough to be pushed by radiation pressure, could theoretically be swept across the vast distances between stars. The major obstacle here is the brutal exposure. Without significant shielding, ultraviolet radiation, cosmic rays, and the extreme cold of space would likely destroy delicate biological molecules in a relatively short time. Still, experiments continue to probe the limits of life's endurance in the open void. The third type, directed panspermia, is the most speculative. It suggests life on our planet could have been deliberately seeded by an intelligent civilization. Crick and Leslie Orgel discussed this in the 1970s, not necessarily because they believed it was probable, but to stimulate thinking about life's ultimate beginnings. Some contemporary researchers have speculated along similar lines, though most regarded as science fiction rather than established science. Together, these three categories form a spectrum, from plausible to possible to purely provocative. They remind us that panspermia is less one single theory and more a family of interconnected ideas, all asking the same bold question: what if life is a cosmic traveler? Why even consider panspermia? Isn't it enough to study life's chemistry right here on Earth? Its significance lies in the grander perspective. If panspermia played a role, it fundamentally alters our understanding of our place in the universe. If life started elsewhere and then journeyed here, then our ancestry isn't strictly terrestrial. Our family tree would have roots extending beyond Earth itself, perhaps to Mars, an icy moon, or even another star system. This would mean biology's story is older than our planet, and that life is not a local anomaly, but a galactic voyager. Another reason is the implication for life's uniqueness. If biology can spread between worlds, then its initial emergence might not be as fantastically improbable as some estimates suggest. Instead of each world needing to invent life from scratch, it could receive a starter kit. This vision makes the cosmos feel more vibrant, interconnected, and brimming with potential relatives. Finally, panspermia forces us to confront the permeability between our world and the great beyond. Earth is not a sealed box. It constantly trades material with the wider solar system. Meteorites fall every single day. Cosmic dust perpetually drifts down. The universe is porous, and if molecules, or even microbes, can survive the trip, then the barrier separating worlds may be much thinner than we imagine. Within the scientific community, panspermia holds a nuanced position. It isn't the widely accepted explanation for life's origin on Earth, but it isn't dismissed as pure fantasy either. It's treated as a legitimate possibility worthy of investigation. Most mainstream scientists agree that lithopanspermia, the swapping of rocks between neighboring planets, is entirely plausible. We have physical proof that it happens, and models indicate that microbes shielded inside rocks could, in principle, survive the trip. The unresolved question is whether any ever actually did. Radiopanspermia, while imaginative, is much harder to substantiate. The radiation exposure and immense timescales involved appear overwhelming for fragile biology. Experiments in low Earth orbit have demonstrated survival for months or a few years, but not the millions of years required to cross interstellar gulfs. Directed panspermia is the least accepted category within the scientific community. It ventures into speculation about alien motives, and without any evidence. Most researchers relegate it to philosophy and science fiction. Caution is essential with fringe claims. Announcements of alien microbes in meteorites or strange rains carrying alleged extraterrestrial cells have almost always disintegrated under rigorous scrutiny, reminding us that extraordinary claims demand extraordinary proof. A common misunderstanding about panspermia is that it seeks to replace abiogenesis, the natural emergence of life from non-living chemistry. In reality, many scientists who discuss panspermia see it as a complement, not a competitor. Abiogenesis remains the most thoroughly studied explanation for life's beginnings. Experiments continually explore how simple molecules might assemble into complex polymers and how those polymers could become self-replicating systems. Panspermia doesn't make these questions disappear. It simply relocates them. If life came from space, it still had to begin somewhere. Think of it like tracing a river. Abiogenesis identifies the spring, the location where chemistry first tipped into biology. Panspermia asks whether that spring surfaced on Earth or on another world. It doesn't eliminate the need for abio. It just changes the address. In fact, panspermia could even make abiogenesis seem more likely. If many worlds were simultaneously running the experiment Mars, icy moons, distant exoplanets, then the overall odds of success increase. Life might have emerged in several places, with only some of those starts finding fertile ground. Earth, in this view, isn't a singular miracle, but part of a vast network of attempts. This synthesis keeps both questions vital. How does life begin? And how far can it journey? Now that we've defined panspermia and its scientific context, we can ask, what evidence exists? This is where the theory shifts from philosophy into the domain of testable science. The first line of evidence comes from physics. We know planetary impacts are violent enough to launch rocks into space. We know meteorites from Mars have landed on Earth, carrying within them distinct traces of Martian chemistry. If rocks can move between worlds, the transportation system exists. The second line of evidence comes from biology. Certain organisms, bacterial spores, lichens, tardigrades, have shown incredible hardiness. They can survive extreme cold, vacuum, and radiation. Experiments on the International Space Station have demonstrated survival for years outside protective shielding. These are clues that biology might be tougher than we once believed. The third line comes from chemistry. Meteorites have been discovered containing amino acids, sugars, and nucleobases, the fundamental building blocks of life. Recently, sample return missions from asteroids like Ryugu and Bennu have confirmed the presence of organic molecules, including uracil, one of the key components of RNA. While these are not signs of life itself, they demonstrate that space is abundant with life's ingredients. And then there are the unresolved questions. Could microbes truly endure the entire voyage, ejection, space transit, and atmospheric re-entry and remain intact? How long can life persist in space before radiation irreparably shatters it? If life arrived here from elsewhere, why haven't we found clear traces of similar life on other bodies? In the sections ahead, we'll follow these lines of inquiry: the mechanics of transfer, the endurance of biology, the potential couriers of life, and the experiments that might finally test the idea. Step by step, we'll evaluate the balance of possibility until we see how close, or how far, panspermia might be from the truth. When a large asteroid strikes a planet, the released energy is staggering. Rock shatters, shockwaves race through the crust, and debris is hurled skyward at incredible velocities. Most of this material falls back down, but some fragments cross a critical threshold. They are launched with sufficient speed to escape the planet's gravitational pull. This is where the concept of spallation windows becomes important. In the upper layers of rock near the impact site, fragments can be blasted free without experiencing extreme heating. If conditions are just right, a piece of rock can break off, accelerate outward, and keep a cool interior, shielding anything hidden within. For biology, this narrow pathway is crucial. Too close to the surface, and the rock vaporizes. Too deep, and it never escapes. But in between lies a window where microbes might hitch a ride to the stars. We know ejection happens because we've collected Martian meteorites right here on Earth. These are tangible proof that material can travel from one world to another. If rocks can move, the next question follows naturally. Can life move with them? Once freed, these fragments enter an environment utterly alien to the world they left. the vacuum of space strips away air and water. Temperatures plummet to a profound deep freeze. Radiation from the sun and cosmic rays bombards every exposed surface. And then there is the factor of time. Journeys between planets can last from thousands to millions of years. For unprotected molecules, this is a death sentence. Ultraviolet light severs molecular bonds in mere moments. Cosmic rays gradually fragment DNA. Yet, inside a sufficiently thick shield of rock, conditions are less hostile. A few centimeters of stone can reduce radiation to survivable levels. Spores, dried and dormant, might last for astonishing durations if they remain concealed. Experiments with spores placed on the exterior of the International Space Station have shown they can survive for years. In the deep interior of a meteorite, survival times might extend into the millions of years. The transit stage is brutal, but not automatically fatal. Biology's toughest survivors could, in theory, drift in silent suspension, waiting for a future encounter. A fragment's epic journey isn't complete until it meets another planet. But this final stage, atmospheric entry, is arguably the most perilous. Traveling at kilometers per second, the rock smashes into the atmosphere, generating a fireball of intense heat and light. The exterior melts or vapor. The shock is tremendous. And yet, once more, shielding is everything. Large meteorites serve as natural heat shields. Their interiors can stay relatively cool even as their surfaces incinerate. If microbes were buried deep within, they could potentially emerge unharmed. Laboratory tests have confirmed this possibility. In one experiment, spores sealed inside artificial meteorites survived a fiery re-entry when returned to Earth on orbital capsules. Landing is the final hurdle. A catastrophic impact can sterilize everything. But smaller pieces, slowed by the atmosphere, can fall gently, scattering across the surface. The odds are slim, but across geological timescales, even slim odds become significant. Arrival is a gauntlet, but not an impossible one. Space is not empty chaos. Orbits, resonances, and gravitational pulls create corridors of movement, what scientists term dynamical highways. When rocks escape from a planet like Mars, their paths aren't random. Many are guided by these highways, steering them into orbits that eventually intersect Earth's. Computer models reveal that transfers between Earth and Mars can sometimes occur with surprising speed. While most rocks take millions of years, a small fraction can arrive within just a few decades. These rare, fast routes are critical because they keep survival windows short enough for hardy microbes to have a realistic chance. Jupiter also plays a key role. Its immense gravity can fling rocks out of the solar system or nudge them inward toward the terrestrial planets. The solar system is dynamic and interconnected, and in its motions, there are opportunities for matter and, perhaps, life to flow between worlds. In 2017, astronomers spotted something unprecedented, a cigar-shaped object tumbling past the sun, moving too fast to originate from our solar system. It was named Oumuamua, a messenger from afar. Just 2 years later, another visitor arrived, Comet Borisov, streaming gas and dust like a typical comet, but on a trajectory that betrayed its interstellar origin. These discoveries transformed how we contemplate panspermia. Interstellar objects are not once-in-a-need flukes. They are likely common, passing through our solar system regularly. If they carry ices, organics, or even dormant life, they could be couriers linking star systems across the galaxy. The numbers are still uncertain, but estimates suggest trillions of such objects wander between the stars. If even a tiny fraction carry the seeds of biology, then the exchange of life between star systems, while improbable for any single rock, might across billions of years be a genuine contributor to life's spread. The most romantic version of panspermia is also the most fragile. Radiopanspermia. In this scenario, tiny spores are so lightweight that the pressure of starlight can push them out of one star system and into the interstellar void. On paper, the physics is sound. Radiation does exert pressure, and dust grains are known to be carried outward on these streams of light. But biology isn't paper. A spore exposed directly to starlight faces a harsh bath of ultraviolet radiation, capable of shredding DNA and proteins in minutes or hours. Cosmic rays add another layer of destruction, relentlessly breaking chemical bonds over long periods. Even if a spore began its journey intact, the timescales involved millions of years to cross interstellar distances make survival seem infinitesimally small. Laboratory tests support this grim outlook. When microbes are exposed in orbit without shielding, most die quickly. A few resilient survivors persist for months or years, but nowhere near the lifetimes required for interstellar voyages. Shielding within ice or dust could improve the odds, but at that point, the mechanism more closely resembles lithopanspermia than the original ethereal vision. This doesn't render radiopanspermia worthless. Instead, it serves as a beautiful thought experiment. It reminds us that the universe is filled with motion, that light itself can propel matter outward, and that, in principle, even the smallest grains can drift across vast gulfs. Whether they carry viable life is another question entirely. The current consensus is that radiopanspermia, while evocative, is unlikely to be the source of life on Earth. Still, its legacy endures as the earliest scientific formulation of panspermia, and as a symbol of the imagination required to explore such cosmic questions. Life possesses a remarkable strategy: dormancy. When conditions turn hostile, certain organisms don't fight the onslaught. They simply pause. Bacterial spores are a prime example. Inside a tough protein shell, with DNA tightly coiled and water content nearly eliminated, they can wait. Heat, cold, desiccation, and radiation all inflict their damage more slowly when metabolism is effectively frozen. Spores have been revived from ancient salt crystals millions of years old, still viable after in geological slumber. Seeds are a parallel wonder. Though more complex than spores, many plants encase their embryos in armored shells with built-in nourishment, designed to endure winters, droughts, and even fires. A lotus seed, retrieved from a dry lake bed, was coaxed to sprout after over 1,000 years. These aren't adaptations for space travel, but they hint at biology's inherent toughness. If an organism can survive entombment in salt for millennia, perhaps it could also endure encasement in rock during a long voyage through space. Dormancy doesn't guarantee survival, but it dramatically improves the odds. The champions of dormancy remind us that life has already evolved solutions for waiting, and waiting, and waiting until conditions improve. Speculation is one thing, experiments are another. To test the limits of survival in space, researchers have taken organisms to the International Space Station and exposed them to the raw space environment. These trials, known collectively as exposed missions, have placed microbes, lichens, algae, and even simple animals outside the station for months or years. The results are sobering yet astonishing. many organisms perish quickly under unfiltered ultraviolet light. Yet when shaded or tucked into protective layers, some survive for years. Bacterial spores, sealed within tiny cracks or embedded in simulated rock, endured up to 6 years in orbit. Even delicate lichens, scraped from earthly rocks, resumed photosynthesis after nearly 2 years outside the station. The Japanese-led Tampopo experiment expanded on this work, specifically studying how microbes might hitchhike on space dust. Microbe samples were mounted on the station's exterior, both exposed and protected, for up to 3 years. Upon retrieval, some remained viable. This demonstrated that microbial passengers could, in principle, endure long enough to move between planets if shielded by even thin layers of dust or stone. What these trials reveal is a gradient of possibility. Bare life, directly exposed, is destroyed by UV light in weeks. But hidden life, sheltered in minute refuges, can endure for years, a timescale long enough for short transfers between nearby planets, especially if dynamical highways expedite the journey. No single experiment has yet proven life could survive millions of years in space. But the fact that survival is measurable at all, even across years in low Earth orbit, transforms panspermia from fantasy into a testable scientific idea. It shows us that biology, though fragile, also possesses unexpected resilience when granted even a slender refuge. For sheer endurance, few creatures rival the tardigrade. These tiny, plump-bodied animals with 8 stubby legs have an endearing shuffle. When conditions become dire, tardigrades can enter a cryptobiotic state called a ton, where they retract their legs, expel most of their water, and nearly halt all metabolism. In 2007, scientists put this resilience to the ultimate test by sending tardigrades into open space. Exposed for 10 days to vacuum, radiation, and unfiltered ultraviolet light. Many died, but some survived, later rehydrating and reproducing back on Earth. This was the first demonstration that an animal, not just microbes, could withstand direct exposure to space, albeit briefly. Tardigrades aren't realistic candidates for cosmic hitchhikers. Their survival times are short compared to the spans required for interplanetary or interstellar transfer. But they serve as boundary markers. If even a multicellular animal can survive days, 2 weeks, then it's not unreasonable to imagine that simpler, hardier forms, bacteria, spores, lichens, might survive vastly longer when protected. Tardigrades remind us that life doesn't always succumb to stress. Sometimes it simply contracts, waits, and emerges once more. Leaving a planet is violent. A rock blasted into space by an asteroid impact suffers crushing acceleration and searing heat. For panspermia to work, life must survive not only space itself, but also the extreme shocks of launch and landing. To test this, scientists have fired microbial spores into rock samples and blasted them with high-velocity projectiles, simulating impact shock. Some spores survived accelerations tens of thousands of times Earth's gravity. The outer layers were sterilized, but deep within cracks and pores, life persisted. Re-entry is another crucible. Temperatures soar as meteorites blaze through the atmosphere, but experiments embedding spores in heat-shielding materials have shown survival is possible. In one test, samples returned from orbit on capsules survived the fiery descent, emerging intact. In another, spores buried inside artificial meteorites endured simulated re-entry in laboratory furnaces. These results point to a narrow but real window of survivability. Not every spore would make it, not even most. But across billions of years, With countless impacts and countless ejections, even rare survivals accumulate. Biology doesn't need certainty or only possibility, repeated often enough. Shock and heat reduce the odds, but they don't eliminate them entirely. Radiation is relentless. Cosmic rays slice through molecules, breaking DNA strands. Ultraviolet light cracks chemical bonds. For biology in transit, the true threat isn't instant death, but the slow, cumulative buildup of damage. Over thousands of years, mutations accumulate until genetic information is scrambled beyond repair. Yet, biology isn't entirely defenseless. Spores contain specialized proteins that protect DNA from disintegrating. Some microbes possess extraordinary repair systems that can reassemble shattered genomes once conditions improve. Deinococcus radio, nicknamed Conan, the bacterium, can stitch its DNA back together even after radiation doses that would be lethal to humans many times over. The key variable is time. If transfer between worlds takes mere decades or centuries, survival seems plausible. If it stretches to millions of years, the burden of mutations becomes overwhelming, even for the hardiest organisms. Transit is therefore a race between the rate of radiation damage and the speed of transfer. Survival depends less on perfection and more on whether the biological clock outlasts the cosmic journey. As scientists have explored the solar system, they've confronted a sobering thought. If life can survive space travel, then our own spacecraft could become accidental couriers. A lander that isn't perfectly sterilized might deliver Earth microbes to Mars or Europa, contaminating the very environments we hope to study. This concern has led to strict planetary protection protocols. Spacecraft destined for potentially habitable worlds are meticulously cleaned, baked, and tested to minimize microbial The rules aren't perfect, no. Sterilization is absolute. But they reflect how seriously scientists take the possibility of interplanetary contamination. Planetary protection is also about reciprocity. If we someday return samples from Mars or Europa, they must be quarantined to prevent the potential introduction of alien microbes here on Earth. Whether or not panspermia has already occurred, its possibility changes how we explore. It reminds us that life, once it exists, is remarkably persistent, and that curiosity must always be paired with caution. Every single day, Earth is bombarded by material from space. Most is invisible tiny dust grains no larger than sand, burning up as shooting stars. But larger pieces also fall. Meteorites that survive their descent and reach the ground. In total, tens of thousands of tons of extraterrestrial matter rain down on our planet each year. These meteorites come in various forms. Some are metallic, forged in the hearts of asteroids. Others are stony, with textures resembling ancient volcanic rock. A precious few, the carbonaceous chondrites, are dark and fragile, rich in carbon compounds. These are the ones scientists treasure most, for they contain chemistry that predates Earth itself. What makes meteorites especially significant for panspermia is their interior. As they blaze through the atmosphere, their outer layers melt and vaporize, but their cores can remain shielded. Inside, temperatures may stay close to the cold of space. Any molecules, or in principle microbes, buried within would be protected during the fiery plunge. Meteorites aren't just falling rocks, they are natural delivery capsules. Each one is a messenger carrying chemistry from elsewhere in the solar system, and occasionally from the galaxy. In 1969, a fireball lit up the skies over southeastern Australia. Fragments rained down near the town of Murchison, and locals gathered the blackened stones. Scientists soon realized what they had: a carbonaceous chondrite, fresh from space and remarkably unweathered by Earth's environment. The Murchison meteorite would become one of the most studied rocks in history. When chemists analyzed it, they found something extraordinary. Inside were over 70 different amino acids, the building blocks of proteins. Many were familiar, matching those used in biology. Others were exotic, not part of earthly life. Their presence showed that complex organic chemistry can occur spontaneously in space, without living organisms. Even more intriguing was chirality. Amino acids can exist in two mirror-image forms, left-handed and right-handed. Life on Earth uses almost exclusively left-handed versions, a mystery known as homochirality. In Murchison, scientists found a slight excess of left-handed amino acids. This hinted that cosmic processes might bias chemistry in the same direction as biology, offering a potential clue to why life favored one hand over the other. The Murchison meteorite demonstrated that meteorites aren't sterile lumps of rock. They are chemical laboratories, frozen records of reactions that occurred before Earth was born. Its amino acids suggested that at least part of life's toolkit arrived pre-made from space. Whether or not microbes ever hitched a ride, the chemistry alone made Murchison a cornerstone in the case for panspermia. Murchison was only the beginning. Other meteorites have revealed different, equally tantalizing treasures. In 2000, a brilliant fireball streaked across Canadian skies and exploded over frozen Tagish Lake. Locals collected fragments that landed on ice, minimizing contamination. Analysis showed Tagish Lake was rich in organic compounds, including unusual hydrocarbons and amino acids. Its composition was distinct from Murchison, demonstrating that different parent bodies in the solar system brew their own unique varieties of organics. The Orgueil meteorite, which fell in France in 1864, is another famous example. It was a fragile, carbonaceous chondrite that crumbled quickly, but it too contained a suite of organic molecules. Early claims that it held microfossils were later debunked, but its chemistry was undeniable. Orgueil, like Murchison and Tagish Lake, carried an inventory of building blocks that blur the line between geology and biology. Together, these meteorites remind us that organics are widespread in space. They aren't flukes, but recurring phenomena. Each fall provides a glimpse into the diversity of prebiotic chemistry scattered throughout the solar system, chemistry that could have primed the early Earth for life. For decades, scientists studied meteorites after they fell, but contamination was a constant problem. Earth's air, water, and life quickly infiltrate fragile samples, casting doubt on what is truly extraterrestrial. That's why sample return missions represent such a monumental leap forward. They collect pristine material directly from asteroids and return it sealed. Japan's Hayabusa 2 mission visited asteroid Ryugu in 2018. It fired a small projectile into the surface, collected the debris, and safely delivered it to Earth. In 2020, when scientists opened the capsule, they found dark grains rich in carbon. Within them were amino acids, nucleobases, and most notably, uracil, one of the 4 bases of RNA. This was the first direct proof that a fundamental ingredient of genetic material exists on an asteroid. Ryugu also contained niacin, or vitamin B3, a compound critical to metabolism. These molecules suggested that asteroids are more than random rocks. They may be reservoirs of biological precursors. NASA's OSIRIS-REx mission to asteroid Bennu took this further. In 2023, it returned samples that are still under study. Early results show abundant organics, including unexpected compounds like magnesium, sodium phosphates. These phosphates are essential to DNA, RNA, and cell membranes. Their presence in Bennu's rubble adds a striking new piece to the puzzle. The chemistry of life is not confined to Earth. It is woven into the fabric of primitive asteroids. Together, Ryugu and Bennu provide the cleanest evidence yet that the ingredients for biology are widespread. These missions don't prove panspermia in the sense of living organisms traveling through space, but they show that space delivers chemistry and perhaps much more. With every sample, the boundary between Earth's biology and the wider cosmos grows thinner, while meteorites and asteroids link Earth to the solar system. Panspermia also raises a more daring possibility: exchange between star systems. For this to happen, interstellar objects would need to carry chemistry or even microbes across light years. For centuries, this was pure speculation. But in 2017, astronomers detected Oumuamua, the first known object from beyond our solar system passing through. It was elongated, tumbling, and unlike anything seen before. 2 years later, Comet Borisov arrived, a more familiar visitor with a gaseous tail. But again, its trajectory revealed an interstellar origin. These discoveries proved that interstellar objects are not rare. Models now suggest trillions drift between stars, with many crossing planetary systems every year. Could such visitors carry organics? Almost certainly. Comet Borisov's spectrum showed carbon-based compounds in its coma, consistent with a rich chemistry. Could they carry dormant microbes? That remains far less likely, given the immense timescales and harsh exposure of interstellar space. Still, the possibility cannot be entirely dismissed, especially if fragments are shielded within ice or rock. The greater significance lies in the principle. If interstellar couriers are common, then the galaxy is more interconnected than we imagined. Over billions of years, material could be exchanged not only within solar systems, but between them. Even if life doesn't leap such gulfs, chemistry certainly can. Every interstellar visitor that passes through is a reminder that panspermia is not confined to our neighborhood. It is, in theory, a galactic process. Of all potential life exchanges in the solar system, the most plausible is between Earth and Mars. The two planets sit relatively close, their orbits bringing them into alignment every couple of years. Both have been bombarded by asteroids and comets for billions of years, sending debris flying into space. Some of that debris inevitably makes the journey from one planet to the other. The evidence is literally in our museums. We have found meteorites on Earth that came from Mars. They are identifiable by their unique isotopic fingerprints. Tiny bubbles of gas trapped inside match the Martian atmosphere measured by Viking landers in the 1970s. These Martian meteorites prove that rocks can travel from Mars to Earth. The reverse is also true. Computer models show that Earth ejecta can land on Mars. But how often does this happen, and how quickly? Simulations suggest that millions of kilograms of Martian rock have landed on Earth over geological time. Some fragments can arrive astonishingly fast within 20 years of ejection. Others may wander for thousands or millions of years before encountering our planet. The quick transfers are crucial. If a microbe is sheltered deep inside rock, surviving a journey of decades is challenging but possible. Surviving millions of years is far less likely. If Mars ever hosted life, its microbes could have traveled to Earth. If Earth developed life first, the same process could have seeded Mars. This raises a profound possibility. that life on both planets, if it exists, may share a common origin. Future sample return missions may one day test this idea, comparing Martian biology directly with our own. Venus is often called Earth's evil twin, similar in size and composition, but shrouded in a thick, crushing atmosphere with surface temperatures hot enough to melt lead. Yet, high above that infernal surface, in the temperate cloud decks about 50 kilometers up, conditions are surprisingly mild. Temperatures are near room temperature, and pressures are similar to Earth's. Some researchers have speculated that microbes could persist in these clouds, drifting on droplets of sulfuric acid. In 2020, a controversial report claimed detection of phosphine gas, a potential signature of life, though subsequent studies cast doubt on the finding. Still, the idea lingers that Venus's atmosphere might be a temporary refuge or even a stopover for life, blown from planet to planet. While no direct evidence yet supports this, the possibility adds Venus to the list of worlds worth watching. If biology can survive in its acidic clouds, panspermia might not require solid ground at all. Far from the sun, icy moons hide oceans beneath frozen crusts. Saturn's moon, Enceladus, has geysers that erupt through surface cracks, spraying water vapor and ice into space. NASA's Cassini spacecraft flew through these plumes and found salts, organics, and, in a stunning discovery, sodium phosphate essential ingredients for life's biochemistry. This means Enceladus's hidden ocean is not only liquid but chemically rich, a potential cradle for biology. Jupiter's moon Europa is another candidate. Its cracked, streaked surface suggests a subsurface ocean. Plumes may also erupt from Europa, though less frequently than at Enceladus. Beneath the ice, interactions between water and rock may provide energy and nutrients, much like Earth's deep-sea vents. For panspermia, these moons matter in two ways. First, they are potential homes for life. If microbes exist in their oceans, geysers could eject them into space, where they might be picked up by passing debris. Second, they are destinations. Rocks or dust carrying microbes from elsewhere could seed their oceans if they penetrate the ice. Enceladus and Europa remind us that habitability isn't limited to planets. Small moons with hidden seas and volcanic activity may be just as welcoming, and perhaps even more likely to exchange biology through their constant venting into space. Titan, Saturn's largest moon, is a world unlike any other. It has thick, golden clouds, a dense nitrogen atmosphere, and lakes and rivers not of water, but of liquid methane and ethane. Standing on its surface would feel surreal. Rivers carve channels across the landscape, but they flow with hydrocarbons in a deep freeze hundreds of degrees below zero. At first glance, Titan seems inhospitable to life as we know it. Water is locked away as rock-hard ice. Temperatures are far too cold for conventional biology. And yet, Titan possesses the raw ingredients. Complex organic molecules form in its atmosphere and rain down to the surface. NASA's Cassini spacecraft detected tholins, tar-like residues made of nitrogen and carbon, blanketing its terrain. Could such chemistry one day lead to life? Some scientists argue Titan is a prebiotic laboratory, showing us alternative pathways to complexity. For panspermia, Titan's importance is symbolic. It proves that life's building blocks emerge even in exotic alien environments. Whether or not Titan hosts life today, it stands as a reminder that the universe is filled with surprising chemistries that could feed into the larger cycle of seeding and exchange. When we look back for billion years, The solar system was not the calm clockwork we see today. It was a chaotic shooting gallery. Asteroids and comets slammed into planets with far greater frequency. The giant impact that formed Earth's moon was just one of many colossal collisions. Smaller impacts were constant, blasting debris into space and scattering it across the inner solar system. In that environment, Earth, Mars, and Venus were not isolated islands, but nodes in a connected network. Material was constantly exchanged between them. Models suggest that in the first few 100 million years, billions of tons of rock moved back and forth. If life or prebiotic chemistry existed anywhere, it would have had ample opportunity to spread. This vision transforms the early solar system into something like a microbial archipelago, a set of worlds linked by constant exchange. Life might not have needed to arise on each world separately. Instead, one successful origin could seed its neighbors, creating a family of biospheres with shared ancestry. Even if life never emerged, the chemistry itself circulated. Amino acids and other organics delivered by comets could be shared between Earth, Mars, and Venus, enriching each world's inventory. The idea of a connected ecosystem shifts the story of life's origins from a single spark on a single planet to a broader drama playing out across an entire region of space. Timing is everything. For panspermia to work, not only must transfer be possible, it must align with the right conditions. Early in the solar system's history, heavy bombardment provided frequent opportunities for exchange. Debris was abundant, and travel routes between planets were shorter and more chaotic. At the same time, planets were cooling, oceans were forming, and atmospheres were stabilizing. These were windows of opportunity periods when environments were becoming habitable, just as the traffic of rocks and organics was at its peak. If life began on one world slightly earlier,